So this is the second unit in Math 20-1. I want to go through a brief introduction about what the unit is about. I mean, it's obviously about trigonometry. That's the name of the unit. But it's a different kind of trigonometry in two regards. There's kind of two parts to the unit. One of them introduces you to a totally new idea with regards to trigonometry. And it's that trigonometry is a tool that can be used in mathematics even though you're not necessarily talking about a triangle. For example, those of you that are in Physics 20, we've talked over the past couple days of classes about the fact that if you use that RCS angle and you know what you're doing, you can find a horizontal component of a vector or a vertical component of a vector without even thinking of a triangle. Okay? And when you stop to think about an angle like 225 degrees, that was an angle we were using this morning in Physics 20, if you did it that way, you were taking the sine of 225 degrees, or you were taking the cosine of 225 degrees. Well, 225 degrees has no business in a triangle, because 225 degrees is greater than all of the angles in a triangle added together. So trigonometry is not just about triangles. There's something called coordinate trigonometry, and that's part of what we're going to be working on in this unit. So everything above this red line, this is on the front cover of your unit handout if you're following. Everything above this red line is referring to what I've just talked about. That there is this notion, and it's a useful one, of applying trigonometric ratios like sine and cosine and tangent to what we call rotation angles, which it turns out, you Physics 20 people, is the RCS angle. That these things mean something, they have applications, and everything above the line is absolutely fundamental to Math 30-1. Like what we do with this coordinate trigonometry, the stuff above the red line, in 20-1 is but a thin layer of what we're going to do with it in Math 30-1. But you need to be really, really proficient at doing it at this level. What's below the line is there's a branch of trigonometry that deals with triangles, but the triangles are not right triangles. So when you talk about a triangle that is not a right triangle, there's no hypotenuse. There's no idea of an adjacent or an opposite side. It doesn't work that way. But we can still use trigonometry to find missing pieces of triangles. We just use something called the cosine law and the sine law, which are not the same as sine and cosine. So when you remember from, say, Math 10, that the sine of an angle is equal to the opposite side to that angle divided by the hypotenuse, that's got nothing to do directly with the sine law. There's a connection, but it's not what the sine law is. Similarly, the cosine law is different. So we're going to get started today by looking at a very basic introduction to what we call coordinate trigonometry, which is all of that trig that is going to resurrect itself in Math 30-1. And I would say everything about this lesson is about terminology. It boils down to understanding, for example, what is the difference between a rotation angle and a reference angle. And if you don't know the difference between those two things, then when I start to explain to you how to solve a trigonometric equation, you won't know what I'm talking about, because sometimes I will say what you've just found is the reference angle, but we want to find the rotation angle. And if you don't know the difference, then you're lost. So we're going to be identifying angles in standard position, sketching angles in standard position, finding reference angles from angles in standard position, and finding angles in standard position from the reference angle. So there's these two main ideas here, reference angles and standard rotation angles. So the Cartesian coordinate grid is something that we use whenever we're dealing with coordinate trigonometry. Coordinate trigonometry deals with angles represented on the Cartesian coordinate grid. That's named after René Descartes, mathematician, philosopher from a very long time ago, who invented the concept of having x and y axes to plot points and to describe mathematical relationships. Specifically, everybody, what a rotation angle is it's something formed by taking an arm, I'll just use my arm, right? and rotating it, which means if you're going to rotate an arm, you have to keep one end fixed, and that's my elbow. So a rotation angle is formed by taking an arm, this arm, which is called the initial arm, and rotating it about a fixed point, which is my elbow. So this angle from my fingertip, if you can imagine a dot in space there that all of a sudden appears, to here, that angle is a rotation angle. This angle from here to here is a rotation angle. This angle is a rotation angle. There's no limit to how many degrees we can go, and there's no set rule about which way you have to rotate. There's a rule for the direction of the rotation and what it means. The only issue with that, and by the way, the final arm, the final location of the arm is called the terminal arm of the rotation angle. Just like when you arrive at an airport, the plane goes to the terminal. A terminal is where your journey ends. Okay? It means final. The only issue with me just randomly showing you a bunch of rotation angles is if I say to you, we have a rotation angle of 40 degrees, and Kale wants to talk about going from here to here, and somebody else wants to talk about, Reese wants to talk about going from here to here, or maybe here to here, we're all speaking a different language. I describe it as being, we don't have rules for which side of the road to drive on. You just drive wherever. And then we have accidents. If we don't follow the same rules in math, we have mathematical accidents. So the rule is that the initial arm always starts on the positive x-axis. This is what we call a rotation angle in standard position. Standard position means we're going to all do the same thing. So whenever I ask you to sketch a rotation angle in standard position, you're going to always start with the initial arm on the positive x-axis and the vertex, which is the pivot point at the origin. So that rotation angle theta is what we're talking about in terms of a standard position. If, and this is going to seem backwards to you, it did the first time I heard this, if the rotation angle starts there and is counterclockwise in direction, which means if you imagine the clock's hands moving around as time goes on, they move in this direction from your perspective. That's clockwise. Going counterclockwise is what I'm showing you up here, and a counterclockwise rotation angle is a positive rotation. And we'll discover more with this a little bit later, but what I'm telling you is, if I said to you about what is that rotation angle, I hope everybody would agree that if I said theta is positive 120 degrees, 120 degrees, that's not far off, right? Are you with me that it's 90 degrees to the top and then maybe another 30? Okay, so that's 120 degrees. If I were to rotate in the opposite direction, then that would be a negative rotation angle. And we can remember why this is a positive rotation angle for now. You won't need to later because you'll just know it. 2, quadrant 3, and quadrant 4. So you're expected to know that those are the numbers for the 4 quadrants. And if you follow those rules, those of you that take Physics 20 with me, and I've shown you that if you use RCS, then you're guaranteed that the x in cosine will be negative to the left and positive to the right. The y in sine will be positive up and negative down. And those of you who aren't in my Physics 20 class have no idea what we're talking about. That's fine. Doesn't matter. So a positive rotation angle starts at 0 and it rotates in a counterclockwise direction so that it passes in the 4 quadrants in the order in which the quadrants are numbered. In fact, that's why they're numbered that way. So as a warm-up on the Cartesian coordinate grid, label the 4 quadrants, label the locations of each of the following angles in standard position, and write a mathematical description of the values that the angles can have in each of the 4 quadrants. So, you know, we know this is quadrant 1. I'm going to choose to put the 1 up here. You don't have to use Roman numerals. You could use traditional numbers. I'm going to put the numbers of the quadrants in the, on the very outside of my diagram. And then quadrant 4 is over here. So we're asked to label 0 degrees, 90 degrees, 180 degrees, 270, and 360 in standard position. Well, 0 degrees is here. It's the starting point. If I take my initial arm and lay it on the positive x-axis and don't rotate it, then I've rotated it 0 degrees by definition. The angle at the top will be 90 degrees. So this is a rotation angle of 90 degrees. I want to be careful here, actually. I might as well introduce this terminology to you. That is the location of the terminal arm for a rotation of 90 degrees. Please don't add this to the diagram, but I just said that's 90 degrees. That's not 90 degrees. Please don't add this. This is a rotation angle theta of 90 degrees. This 90 degrees at the top is simply telling you that's where the terminal arm will end. That's where the rotation ends. If we continue another 90 degrees, this is 180 degrees, another 90, and this is 270. Another 90 takes us back to 360 degrees. So 0 degrees is a different rotation angle than 360 degrees. That's a fact. Let me say that again. 0 degrees, even though it lands in the same place as 360, 0 degrees is a different rotation angle than 360. They share the same terminal arm, though. And for that reason, these angles, and it's not part of the question, but I'm trying to help you out here for next year as well. 0 degrees and 360 degrees are co-terminal. It means they share the same terminal arm or the same termination point. You don't have to add this to your diagram, but if you stop and think about it, it should make sense. This that I'm labeling as 540 degrees is the location where 540 degrees terminates. Because if I go all the way around to 360 and add another 90, 450? 450, my mistake. If we put 360 plus 90, which is 450, can you just double check that? My mind is not good today with numbers. Oh, yeah, that's right. Okay. We would say that 450 degrees is a different rotation angle than 90 degrees. It is different. But they're coterminal. There's no difference, by the way, and I'm just exploring different things with you here. You don't need to know all of this in this unit. But there's no difference, by the way, between the two angles in terms of trigonometry, because if I were to take the sine of 90 degrees, I happen to get the number 1, and you'll learn why later. And if I take the sine of 450 degrees, I get the number 1. You can take any two angles that are coterminal. Would you agree that 300 degrees would be a rotation angle that would start here and go around to about here? Would you agree that that's the same as negative 60? Because 300 will go around and it will come up 60 degrees shy of being a full revolution, so I could use negative 60. Two different angles, they are different, but they're coterminal. If I take, say, the cosine of 300, I get that. If I take the cosine of negative 60, I get the same number. If I take the sine of 300, I get this number. If I take the sine of negative 60, I get the same number. And you know, that after you see that demonstrated to you, you probably go, well, why do we call them different angles? Because they do have different meanings. It may be hard for you to appreciate that right now, but we're building on skills that go into grade 12 and into calculus, and they do have different meanings. So we've labeled all of the rotation angles. For each of the 4 quadrants, write a mathematical description of the values that the angles can have in that quadrant. So what is the, we're going to say, domain of values of theta in quadrant 1? Well, theta, if it's in quadrant 1, has to be more than 0, correct? Because 0 degrees is not in quadrant 1, but it has to be less than 90. And I feel as though this needs a little bit of time to sink in and some discussion. What I'm saying is theta has to be more than 0 degrees, and theta has to be less than 90 degrees, right? You're good with that idea? Okay, well, I want you to notice that if theta is greater than 0 degrees, then 0 degrees must be less than theta. Run that through your brain a few times. Just really think about this and convince yourself that they're saying the same thing. If I were to look on a number line, here's 0, and this statement is saying theta is over here. It's greater than 0. If I were to look at this statement, here's theta, and it's saying 0 is less than theta. It means the same thing. I would normally explain this with numbers, and I will do so right now. If I told you that x is greater than 8, and you look at this statement in a mirror, this is what you would see, isn't it? And it says 8 is less than x. So all I'm doing is I'm reading this backwards. And that becomes important because I can do this now. I can put these together into a single statement. How many of you have seen this before? Maybe your Math 10 teacher showed it to you. Maybe they didn't. We would write here that 0 degrees is less than theta, which is less than 90 degrees. This is merely a way for me to tell you that this is the minimum value of theta, and this is the maximum value of theta. And theta is somewhere in between. But it's always minimum, less than, variable, less than, maximum. If we use that same notation in quadrant 2, the minimum value of theta in quadrant 2 would be 90 degrees. The maximum would be 180 degrees. And I want to be careful here because it's when I say the minimum is 90, I'm actually saying it can't be 90. It's got to be more than 90, right? So we would do this. Always less than, less than. In this quadrant, it goes from 180 to 270. So we can write 180 degrees is less than theta, which is less than 270 degrees. And then finally, in this quadrant, we would say 270 degrees is less than theta, which is less than 360 degrees. For all of those, you need to put the degree symbol. If you don't have a degree symbol, you're telling me it's radians, and we don't know anything about radians yet, and we won't find out anything about radians in this course. It's Math 30. The actual Math 20 content in this lesson is very minimal. I've designed this lesson so that I can take some time to teach you some other things that you need to know down the road. One of them is this notation, right? So, which is new to some. How many of you would you say it's new to you? You haven't seen it before, or you don't remember, okay? And that's fine because it's not part of the Math 10 curriculum. If your Math 10 teacher showed it to you, he or she just was helping you out a little bit. But there's another notation that we can use. And I feel as though we have time today, so I'm going to show it to you. It's that. And that I know this is going to be difficult for some people because it looks like I'm saying x comma y, but it's not. I'm saying theta has a minimum value of 0 and a maximum value of 90. But these round brackets indicate that theta cannot equal 0 and cannot equal 90. Okay? So if I told you, and again, I think this is valuable. If I told you that I have, we'll use x. 4 is less than x, which is less than 10. What I'm telling you is that what I'm going to draw in red represents the values that x can take on. Are you with me on that? Okay. I could write that as this way. And I like to put an x in front just to tell you what it is, but you don't have to right for now. Okay. If this were the case, then this would be what it would look like. Just ponder that statement now. That this is saying 4 can be less than or equal to x, which means x can equal 4, and x has to be less than or equal to 10, then this red diagram above it would tell you the domain of values of x, yes? Well then, we would use square brackets. Just to look ahead, that's all. We're just looking ahead and thinking, well, when we finally really get into this in a further unit, you will know what I'm talking about. It won't require as much time to explain. Okay. We could also put, from 90 to 180. We could go from 180 to 270. You're getting the idea, I think. 270 to 360. And I admit, warm up A, B, and C is just as much for you to get used to this notation and to become familiar with that grid in terms of angles. Any questions with A, B, or C? All right. So now let's talk about some specific terminology. What a reference angle is, and it has its uses. It's not very specific in terms of, I know where the terminal arm is. You don't, by looking at the reference angle. It's simply the smallest angle between the terminal arm and the x-axis. It has no direction. It's never negative. It's just an angle. And for this reason, well, I'll get to that later. So, a reference angle is the smallest angle between a terminal arm and the x-axis. Examples. Sketch a rotation angle of 60 degrees. It's always implied that it's in standard position. So I'm going to hand out some rulers. Let's be somewhat neat in our work here. So I'm going to show things up here that I don't know that you want to draw. When we draw, so maybe don't draw anything just yet. Let me show you what we would draw if we wanted to be pedantic about it, which means by the books, as picky as you can imagine. We would draw an initial arm, and then we would take that initial arm and we would rotate it counterclockwise 60 degrees. That's what we would draw. Okay? What I'm telling you is, I don't think we need to draw the initial arm all the time. We all know where the initial arm is. It's on the positive x-axis. So I think what you need to draw, and we're not going to get out the protractors, but is a terminal arm that looks like that. And we're going to label this rotation angle as theta equals 60 degrees. I hope everybody is clear, and this isn't just picky for pickiness sake, that that rotation angle has a direction. The arrow I drew, that arc, has an arrow on one end of it indicating the direction of the rotation. Okay. So, the rotation angle is 60 degrees, and I am going to tell you this now. It's just going to save so much time. That whenever you see theta, it's the rotation angle. We don't have to write theta sub rotation. Okay? So that's the rotation angle. Now the question says, what is the reference angle? Well, the definition of the reference angle, and it's right at the top of the screen, is that it's the smallest angle between the terminal arm and the x-axis. Well, this is the x-axis. I'm just in teaching mode. There's no need to draw anything here. So, can I measure an angle between that terminal arm and the x-axis? Yeah, I could. I could measure this angle. That is an angle between the terminal arm and the x-axis, but it's not the smallest one, is it? The smallest one is this. And I'm going to label this as theta reference equals, and it's at this point you go, man, are you kidding me? What's the big deal? It happens to be 60 degrees, doesn't it? But notice that arc does not have a direction. A reference angle should not be thought of as directional. It's just a number of degrees between the arm and the x-axis. That's it. Example 1A and B. Any questions with that? Okay. What if we had a rotation angle of 150 degrees? And this plays well into the RCS thing in Physics 20 from the past few days, if you're in Physics 20. We know that a full rotation of 180, if you look up here, a full rotation of 180 takes me to here. And if you're watching on video, I just rotated my arm from pointing along the positive x-axis all the way 180 degrees to pointing backwards. But 150 degrees is 30 degrees less than that. So that means when I sketch this rotation angle, I should try to sketch this so that that terminal arm is about 30 degrees up from the x-axis. And then I can put in here theta rotation equals 150 degrees. What is the reference? The reference, theta reference, is 30 degrees. And again, it may seem insignificant, but it is important. Otherwise, I wouldn't be harping on about it. Your reference angle has no direction. When I label it with a little arc, it's just an arc. It's got nothing else to it, no arrows. You can see that the reference angle and the rotation angle add up to 180, and that will always be the case if we're talking about termination in quadrant 2. Colin, are you with us? Okay, just checking. Sketch a rotation angle of 225. Well, in my mind, I know 225 is between 180 and 270. The question is where, how far between? So what I would probably do is take 225 and subtract 180 from it to know how much further past 180 I need to go. And I think it's 45. And 45 is halfway, angularly speaking, halfway between 270 and 180. For some reason, it must be part of my brain. I very often have a difficult time. Does that look like 45 degrees to you? It's close enough. I'm always second guessing myself, and then I increase it and I decrease it. So let's label the rotation angle right there. This is theta rotation equals 225 degrees. The reference angle is 45 degrees. I think we're picking up on this, are we not? Okay, good. One of the reasons why we need to know about the reference angle and its relation to rotation angles is when we solve trigonometric equations, and we will later in this unit, you're going to have a step that involves using your calculator to find an angle. And the angle that your calculator will spit out to you will not always, in fact very rarely, will it be the rotation angle, which is what we're after. It will tell you the reference angle. Okay. And we're obviously going in the 4 different quadrants, 310 degrees. With a little bit of thought, I hope that you understand that it is going to be 50 degrees shy, 50 degrees shy of a full revolution. Right, 360 minus 310 is 50, which, by the way, indicates that the reference angle is 50 degrees. The rotation angle is 310 degrees. I would tell you that if you ever have to do a problem on a written response, and this happens in Math 30, that if you have to draw your diagram, you should probably get a protractor out and draw it half decent. I don't know how I did there. Not bad. Pretty close. Whoop. So any questions with 1 through 4? Okay. Rotation angle in standard position has a reference angle of 32 degrees. What are the 4 possible rotation angles? And this, I think, is it. This is the last thing we're going to be looking at today. So you're going to have some questions from your textbook to work on, and I will hand back your exams so you can spend some time looking at them. I do not go over exams question by question, and you're not always going to have a lot of time to look at them. So if you ever need more time to look at your exams, you have to do that at lunch or outside of class. Well, if we had a rotation angle that terminated in quadrant 1, then it would look like that. I know it looks approximately like that because the reference angle is 32 degrees. So this is 32 degrees. I'm just using green for the reference angle. I know you don't have a green pen, but that's what I'm doing. If I had it in quadrant, and there's no order to what I'm doing here, if I had this in quadrant 3, I hope you notice or would know that the terminal arm in quadrant 3 with a reference angle of 32 degrees will be parallel to the one in quadrant 1. In other words, if I drew these both on the same grid, they would be 180 degrees apart. So this would be if it's in quadrant 3, this is 32 degrees for a reference angle. If it were in quadrant, we'll go to 2 now, this would be the reference, and if it were in quadrant 4, again it would be parallel, this would be the reference. So your job, in the first set of examples, 1 through 4, your job was, here's the rotation angle, what's the reference angle? Here, what I'm saying is, here's the reference angle, what's the rotation angle? So you need to be able to figure out what theta is, what theta is, what theta is, and what theta is. And, admittedly, I think I've kind of alluded to this or mentioned it. This lesson is more about you just getting comfortable with the terminology and the idea of rotation angles on a coordinate grid. Some high school math students like rules because they are memory hounds. That's not an insult. The rule is that if you're talking about quadrant 1, I'm going to write quadrant 1. I'm writing it over here just because that's where I have some space. Then the reference angle is equal to the rotation angle, right? They're the same thing, except one has a direction. So in this particular case, that means that this rotation angle is 32 degrees. If you're talking about in quadrant 3, and again, I'm not a memory kind of person. I have to either draw this or visualize it in my head. Then the reference angle plus 180 will equal the rotation angle. And we have to go 180 and then add that reference angle. And that means, just confirm that for me, please, that 180 plus 32 is 212. Yeah? Okay. If we happen to be over here in quadrant 2, what's the relationship between the two? Well, you have to take 180 degrees and subtract the reference angle to get the rotation angle. And by the way, there are other ways to write these things. I mean, this statement that I've just put here in the top right corner, I could have written that the rotation minus the reference gives you one, or the rotation taken away from 180 gives you the reference. There's different ways you can write it. Anyway, if we take 180 and subtract 32, get 148. Thank you. 148 degrees. And finally, if we're in quadrant 4, I think it's pretty obvious that the reference angle in quadrant 4, will be equal to 360 degrees minus the rotation angle. Or 360 minus the rotation angle would give you the reference. There's other ways you could write it. The goal is, if I give you a rotation angle, you can find the reference angle. Even if I give you a rotation angle of... So there are some questions for you to work on. I'm going to just get a couple of things done here quickly. It looks like you have about 20 minutes.